All right, we'll go ahead and get started. Today we'll talk non-parametric bootstrap. Wednesday we covered parametric bootstrap, which says we are making parametric assumptions about the population. So, for example, we would say that we believe the population follows a normal distribution, and we generate samples from that parametric distribution. Or we say, we believe the population has this distribution, and we use kind of R's built-in functions to randomly generate values from a specified population. In non-parametric bootstrap, we do not make those kinds of assumptions about the population. Instead, we assume that the random sample that we have is representative of the population. And so to kind of recreate our quote-unquote population, all we do is we just duplicate the random sample that we have. We duplicate this like an infinite number of times, and that produces kind of this pseudo sort of population. And then we can draw from that population to generate a sampling distribution. And so that's effectively the same as sampling with replacement. So when you sample your current sample with replacement, it's effectively the same as making like a million copies of your current sample, or an infinite number of copies of your current sample, and then drawing samples from that population. And again, all of this is so that we can generate a sampling distribution and thus compare our current observed sample to what we saw, to the sampling distribution. Okay, so we're going to continue on in this Latino education achievement data set. And again, the thing that we are exploring is to see if there's any difference in the mean education achievement level of immigrants from Mexico versus immigrants from other Latin American countries. Okay, and once again, kind of our summary statistics is this. So we have 34 people from countries that are not Mexico, 116 from Mexico, and this is their mean education achievement level and their standard deviation. And so we observe a difference of around 5.9 points between these two groups. Okay, and unfortunately we don't know what those numbers mean. Okay, but anyway, we are doing a hypothesis test, and our null hypothesis is that the mean education achievement levels of both groups is equal, so that there's no difference between them. Okay, and then the alternative is that they're different. And under the null hypothesis, we are effectively saying that both values, the values that we see for the Mexico group and the values that we see for the other countries group, those values are coming from the same population. Okay, and so the non-parametric bootstrap is done almost in the exact same way as the parametric bootstrap, except when we draw our values from the population, we're not drawing it from some specified distribution like R norm or R's random whatever value generator. We are just going to resample our sample with replacement. Okay, and so this is what our thing looks like. Okay, these are just comments to explain what's going on, but really it's just like 4 lines of code here, other than setting the seed and creating a vector to store your values. Okay, so it's just a for loop, and then inside the for loop there's three things, and technically you could even just put these inside here and just have 1 line. But here we say the group for Mexico is we're going to use sample, and we're going to take that column, Latino $achieve. So these are the achievement scores, and we're going to draw 116 values with replacement. Okay, so currently this column has 150 values, And by doing sampling with replacement, we're just taking those 150 values, duplicating them like a infinite number of times, and from that large population now we draw 116 values. Same thing over here, we're just drawing 34 values so that the resulting samples are of a size analogous to our original data. And then we are calculating the mean of this group and the mean of this group. Okay, and we calculate the difference between them because that's how we got this value 5.9. Okay, that's the mean of, I guess I have it backwards. It should be the mean of 0 minus the mean of the other. Okay, but I mean, I guess, well, because it's non-directional, whether it's positive or negative doesn't really matter. But you know, we're just taking the mean between difference between these two means. Okay, and so this is non-parametric bootstrap. All right, is this okay? All right, and so again, we have a non-directional or two-sided alternative. And we just say, okay, we're going to take the absolute value of these differences that we generated. So this diffs vector is just a bunch of values that we've observed while the null hypothesis is true. Okay, and we say, okay, well, how many of these are greater than or equal to the observed difference? And we get 0.0469. And that kind of agrees what we get with from the parametric bootstrap and the t-test. They're all kind of in agreement, just under 5% here. Okay, and that's that's basically non-parametric bootstrap. I want to get into library boot, okay, or package boot, and just kind of talk about other scenarios in which we would apply non-parametric bootstrap. Okay, so here we have it for comparing two groups, and here I will do the same thing but using package boot. Okay, so I would say so this is perfectly valid, but if you ever are in a situation where the bootstrap, the statistic that you're going to calculate depends on more than one variable, you probably want to use package boot. Okay, so over here we're just looking at one column, the achievement level column, and so this is fine. You know, resampling from that column is no problem, but sometimes there might be a situation where you want more than one column to calculate your thing. So, but anyway, library boot, okay, has this primary function called boot, and there are three arguments you need to provide: the data that we are going to do bootstrap with, and then the statistic to be calculated, which is going to be some kind of function that we have to define. Okay, maybe I should put that in. The statistic to be calculated, and this is a function that we define. Okay, and then the number of replicates are, so usually like 5,000 or 10,000 or something like that. There's other arguments, but they all have default values associated with them. Okay, and so one thing to keep in mind is that when you use boot, it does something a little bit clever in that it doesn't actually resample the values themselves. It resamples the indices in the data. Okay, so in our case, so when we did bootstrap, when we did non-parametric bootstrap over here for the Latino education data set, we said take this column, Latino $achieve, and then draw a sample with replacement from it. Okay, but what boot will do is that it says, oh, you have 150 rows in your data set. Okay, so now over here I'm going to take the vector 1 through 150 and I'm going to just resample 116 values out of this vector of 150. Okay, and that's going to indicate these are the people I'm selecting. And so because you're sampling with replacement, you might select some people more than once. Other people don't get selected at all. And then we subset the data, the Latino $ achieve, and we subset it with the indices that the function boot generates. Not we don't do the resampling of values directly in boot itself. Okay, and so what this the advantage here is that if your statistic is something like correlation, which involves 2 columns of data. Okay, if you tried to do it the manual way and you separated. If you resampled one column and you resampled the other column kind of independently, you're going to break any kind of correlation that exists between them. Okay, and so what needs to happen is you need to say, I'm going to sample kind of these rows together. I'm going to take row 2 and row 15 and row 7 and row 128, and you're taking kind of both values from each column. For each row that you are doing, okay, and that's what boot allows us to do. It resamples the indices and pulls out the corresponding rows in the data, and thus it will maintain any kind of relationship that exists between columns. Okay, so that's what we do. I mean, of course, you could take a queue and implement this manually yourself, but I would say Boot is a fairly popular package for conducting Bootstrap, and therefore I think it's worth learning, especially if you intend to do any kind of bootstrapping yourself. Okay, and so the most important thing when you do this bootstrap is you have to be able to define this function, the statistic to be calculated, and you'll get a little bit of practice in your homework, and so definitely read through that and look at these notes here. Okay, and so again, what we're trying to do is we're trying to calculate the mean education achievement level of basically 116 values from the column that are going to kind of represent our group from Mexico, and then 34 values from the column that's going to represent our values from other countries. Okay, and then whenever we write a function for this statistic, there's always going to be 2 arguments. Okay, so your function is always going to be an argument of the data and the index. Okay, if you specify your function any other way, it's gonna break. Okay, because this function boot itself is expecting a function of 2 arguments, and it's going to try to put in 2 arguments into that function. And if you give it something that's it doesn't work that way, it's gonna crash. Okay, so this is what our function might look like. Okay, it's a function of the data and the index, and I've called this the difference function. Okay, let me just see if I can make this a little bit bigger for you guys. And so I wrote this in kind of too many lines just so it's easy for you to see. I could have done this in 1 line, but just to kind of make it easy to see, the first thing I do is I subset data, because that's one of the arguments. So, and I subset the data using the index. Okay, so Bootstrap will provide this argument data, and we'll provide this argument index, because when we call boot, we will specify the data and we specify the function, and what boot does is it then takes the data that we've specified, passes it to this function that we write, and then boot will also pass the argument index into this function. And so what boot will do is you'll say the data we want to do is Latino education, and then boot will say, oh, there's 150 rows in that thing. These are the indices of the rows that I want to use in my Bootstrap resample. Okay, so it's going to do that, and so what we need to do is we need to then subset this data accordingly. Okay, and so I'm creating kind of a new, I'm creating a new data frame where I've just selected the rows from data using only the indices that Bootstrap has passed to me. Is that okay? So this will subset the data to just kind of 150 new rows that have been resampled. And from there, I'm going to take kind of the first 116 and store them in Mexico, and take the last 34 and store them in group other. Okay, and then the last row, last thing that gets evaluated is going to be the value that gets returned by the function, and that's going to be the difference between the mean of the Mexico group minus the mean of the other group. Okay, and so this is going to be the function that that we apply here. Okay, all right, and then to run the boot is you say you run package boot. You say data is equal to the data frame we're using. In this case, we've stored it as Latino. And then the statistic is this function that we've defined, diff func, okay? The difference function. And we say do this 5,000 times, or you can do 10,000 times, or whatever you want to do, okay? So boot results will be the output of this thing. And so let me just kind of run this for you. So when we look at boot results itself is a list of a whole bunch of things. Okay, it's a list of 11. It comes with T0 and T and all of this stuff, okay? And it says you know, this is what we end up getting here, okay? And basically all of the resampled things show up in this vector boot results $T. So this is going to be kind of the different values that get resampled. And so one for each replicate. So we have a vector of kind of 5,000 things, and they're all stored in here. And so what I've done here is I've drawn a kind of a histogram of the different the differences that we've observed, which are centered at 0, which is expected because under the null hypothesis, both groups, you know, group 1 with 116 and group 2 with 34, they're coming from the same population, so we expect those differences to be centered around 0. And so, you know, the mean is just a little bit different. At it's close to 0, but negative 0.036. The standard deviation is this, and here we can ask of these values, how many are greater than or equal to our observed difference, you know, the absolute value, and we get something around just under 5% as well, okay? And again, you know, with boot, it's easy. I can just crank this up to 50,000. Let's see, I don't know if that's going to make any kind of difference. It'll take a little bit longer to run. Uh-oh, did I break my computer? Oh no, okay, it's done. And then, okay, and then if we do, if we calculate those things, we see the mean is even closer to 0, and then the kind of our p-value is 0.04766, which is in agreement with kind of all of the other things that we've seen as well. Okay. I'm going to go ahead and I want to talk a little bit about homework 6 and just talk about the bootstrap stuff that has happened that's going on in homework 6. Okay, so here there's another package called bootstrap, but we're not actually going to use the the functions in package bootstrap. We're going to just use the data that shows up in package bootstrap. So there is a library called bootstrap which does bootstrap stuff, but as far as our functions go, we're going to just use there's no package called bootstrap. All right. Guess I have to reinstall this or something. Okay, let's try this again. All right, so inside package bootstrap, there is a data set called law82, okay? And so this is our data set that we're going to look at. And in this, if I remember correctly, this data is fairly old, okay? Well, I guess it came from 1993. Okay. This is data from 82 different law schools, and this says the universe of 82 USA law schools. So this, apparently, this is supposed to represent all the entire population of law schools that exist. I think there's more than 82 in the United States, but I don't know, maybe at the time there was only 82, I don't know, okay? So Law 82, this provides the population, and what we are interested in is there a correlation between someone's LSAT score and their GPA, okay? And I don't know anything about the LSAT, nor do I know anything about GPA. I mean, these seem really low, right? I don't know, right? I don't know. Maybe there's just been great inflation since 1993, and you know, the students kept hammering at their professors, and the professors relented and gave them higher grades. I don't know. So anyway, this is supposed to represent everybody's LSAT and GPA scores, all right, and this is what we have. And so we see there's a correlation between LSAT and GPA, and in general, higher LSAT corresponds with higher GPA. I think this was it just is a numeric vector. This is not very helpful, this data file. LSAT is the average score on the LSAT exam and the average undergraduate GPA, okay? So this is for, I guess, kind of admission information for what these different law schools accepted. Okay, and so what we see is in the universe, okay, there's a correlation of around 0.76 between LSAT and GPA, okay? The correlation between LSAT and GPA is around 0.76. What we are going to do is we are looking at a random sample, okay? So if I do law, not a law 82, this is a random sample of 15 schools taken from the population of 82, okay? So we're just randomly sampling 15 out of the 82, and we're going to see, you know, can we estimate the kind of the population correlation based on our random sample here, okay? So if we look at our random sample of 15, our random sample is around 0.776, okay? If over here, what I've done, this is similar to what Bootstrap does, is I'm sampling 15 rows from the 82, but here I'm just randomly sampling 15 without replacement to kind of generate different sample. And so using different seeds, we can see that if I selected 15 different schools, the correlation can be quite different. So here I get a correlation of 0.95. This is just by random chance of selecting from the 82. I selected 15 new ones, and I'm getting something different. Here, if I select 15 different ones, I get a correlation of only 0.63. If I select 15 other ones, something happened. And I get a correlation of 0.817, okay? So just by selecting 15 different schools out of the 82, we can see, our values change quite a bit. But anyway, we'll just go ahead and we'll take the data set law, which has 15 things, and we'll go ahead and use package boot, okay? And so what we're going to do is we're going to resample our 15 schools. So this is our 15 schools in the small sample, okay? We're going to resample this a whole bunch of times. And again, the presumption in non-parametric bootstrap is that these 15 schools are representative of the entire population of 82. Okay, and so we're going to just resample these 15 over and over and over again and see what kind of values we get. Okay, and so what we do is we take the data, which here is going to be the data frame of 15 rows. Bootstrap is going to pass us an index of, which of the 15 rows to select, and we'll subset it that way, okay? And we'll say we're going to just take column LSAT, column GPA, and calculate the correlation between the two, okay? And again, we could do this just in one row if we're a little bit more, want to be concise, but that's fine, okay? And so here I'll do library boot, and we're going to do bootstrap using the dataset law and our correlation function, and here I'll just do 500 replicates, okay? And so here's kind of the results. This is the summary that it produces, and here we're interested in the kind of the standard error of the sampling distribution, okay? So we're going to take results $T, and we'll just ask for the standard deviation of that. And it gives us a standard error of 0.138. Okay. We could do this for any of our other samples, and so again we saw different things, and we get drastically different standard errors. Okay, and so this is a tiny bit worrisome, but it also just kind of illustrates the dependence upon your sample being representative of the population, because that's the key assumption that Bootstrap is making, which in the long run should be an acceptable proposition, because if you've got your sample via random sampling, we have no reason to believe it not to be representative. But seeing how our standard errors vary quite a bit, our standard error estimates vary quite a bit from each other, it also kind of gives us some caution about what we can do. Okay. The last task in your homework is to kind of look at this speed of light information from the 1880s. Okay, and this is actually like, it's rather it's a rather remarkable idea that they had. This was these people were very creative. So you think back to the 1880s, which they don't have the ability to measure. Nobody has a stopwatch that can measure in microseconds or nanoseconds, right? But somehow they are able to get measurements like 24,828 nanoseconds or 24 microseconds, okay? How did they come up with something like this, right? Because they're trying to measure basically how long it took light to bounce from a mirror. So this guy, he worked at the Naval Academy and in DC, in Washington DC, and he puts a mirror on at kind of Washington Monument, which is about 3.7 kilometers away, and so the round trip distance is about 7.5 kilometers. Okay, and so he doesn't have, he can't just like shine a light and say like, oh, I saw it bounce off and it came back, right? It's not like shouting an echo or something. So the way they did this was, I don't know if you can see here, but they had this this mirror that was spinning. Okay, the mirror spun, and basically, in order for the beam to come, this mirror is spinning like 200 revolutions per second. He shines a light. Okay, they don't even have lasers back then, so he just shines a light. The light bounces off of this spinning mirror, and as it travels, basically 7 kilometers, okay, and or 3.7 kilometers this way, it hits the mirror, it comes back, so it's traveled about a total of 7.4 kilometers. In that time, the angle of the mirror has shifted ever so slightly, okay? And by being able to know the speed of how much the angle of the mirror has shifted, and seeing where the light then bounces off, they were able to judge the speed of the light. So they're looking at how fast the mirror is spinning, and so basically, the light first hits the mirror, it bounces off, and it goes down. It travels 7.4 kilometers, and in that time, this spinning mirror has shifted ever so slightly, and they've set it up so that if the angle of the mirror was wrong, the light wouldn't reflect back. But if the angle of the mirror was correct, then the light reflects back, and they can see it. And by kind of taking that into account, they're able to figure out how fast the speed of light has traveled, which is a rather remarkable thing. You should look up basically Mike Mickelson's and Newcomb's speed of light experiments on YouTube and stuff. It's pretty creative. Okay, but anyway, and they managed to get pretty good accurate measurements. So the current accepted speed of light value is 299,792 kilometers per second, and I think their estimate was like 299,810 and 299,860. So they were off. They were off, but pretty good. Okay. So anyway, what we're asking you to do is to see if the values you have differ from the accepted value, which should be 33. Okay. And so the way you are going to do this is you're going to take your kind of I think the 62 observations that you have, 66 observations that you have, and which has a mean of 26.2. What you're going to do is you're going to recenter that data to 33, which is kind of the accepted value, right? And so under the null hypothesis, the mean of our data should be 33. And so what we do is we're going to, for Bootstrap, we recenter our data so that it is centered at 33, okay, which is what the null hypothesis says should be the case, okay? So we're going to say, assuming that the null hypothesis is true, what this data now informs us about is the amount of spread that exists in our data, okay? And we're going to say, based on the amount of spread that we see in our data, is it possible that if it's truly centered at 33, can we get our average of 26.2? Okay, so we recenter our data so it's centered at 33, and we say based on assuming our null hypothesis is true, which is why we center it at 33, and we say, and given the amount of spread that we've seen in our data, is it possible to get a mean of 26.2. And you'll have to do a bunch of bootstrap resampling. It's going to turn out your p-value is going to be quite small. Okay, so it is possible, but it's unlikely. So indicating that, you know, their measurements, whatever they were doing, there's probably something a little bit off. Okay, they got really good, but something was you know, just a tiny bit off, and so they were unlikely to ever actually get this actual true value of 33. Okay, and then I just have you do it again by removing some of the outliers that we see here. But anyway, that is kind of this package boot and the idea of non-parametric bootstrap here. Okay, let's see. Next week is 10th week, and I think I've covered what I want to, like the primary stuff I wanted to cover in this class, okay? And so next week on Monday, I'll talk about the final exam. And then Wednesday and Friday, I'll have, I don't know, what I think is some kind of fun ideas in computational statistics, and we'll talk about those things. But you don't have to worry about the stuff on Wednesday or Friday being tested. But come, and I hope they'll be good to see. So anyway, this is it for week 9, stuff like that. I think I think instructor evaluations are out now, right? So please fill those out. Anyway, I hope you've enjoyed the course so far, okay? And please fill out those instructor evaluations. They're very useful. I'm willing to do this, okay? I will give 1 percentage point of extra credit for if the entire class as a whole achieves over a 70% response, okay? So it's either the whole class gets this 1 percentage point of extra credit or not, and as a whole the class has to achieve a 70% response rate, okay? So we'll do that. So respond to your thing, and either the class all gets their extra credit point or not, okay? All right, we'll end there. So.